of these objects, of these protocores, it's the time for them to cross orbits and merge depends exponentially on the number of Hill sphere spacings. This K is just this orbital spacing measured in Hill radii. For mergers to happen, you need this merger time scale to be less than the circularization time from gas dynamical friction, which scales as 1 over the gas surface density. And then you just solve for the gas surface density required. But that depends on knowing what K is, right, the spacing. And this is just one of the amazing measurements from Kepler that we actually have statistics on K, that in multi-planet systems, they're separated by there's a spread, about 14 Hill sphere spacings, okay, with a spread. And so if you're interested in the last doubling, and I should be really more precise about what I mean by formation, right? What I mean by formation here, when I say that super-Earths form late, what I really mean more precisely is that it last doubled its mass late. So if I'm interested in forming a 10 Earth mass object, I'm interested in the last few doublings, how it went from 2.5 to 5 to 10 Earth masses. Those last few doublings occurred late in a gas-poor environment. And so if you're interested in the last doubling, you take this 14, which is the spacing today, and just divide by 2. Not quite 2, 2 to the 2/3, because the Hill sphere also goes down by 2 to the 1/3, right? Okay, so there's a spread, and here are the gas surface densities required. This is the amount of depletion required, and like every good astronomer, I'm going to plot things backwards. So this is the surface density relative to the minimum mass value, and going up means greater depletion. Okay, so here are the curves for various values of K. Everything above these lines is good for mergers. If K is 7, then you need to reduce the surface density by about 4 orders of magnitude relative to the minimum mass value. Okay. What if the spacing is larger? Then you need something like 10 to the 7. So these are pretty gas-poor environments. Gas-poor, but not gas-empty, because you know they have a little bit of gas. Now, the planets do. So I can overlay on this plot a separate but related consideration. You know, gas dynamical friction not only circularizes the orbits, but it also induces orbital decay. Right? We call this type 1 migration. But it's just gas dynamical friction, familiar to anyone who studies galaxies, right? So it also induces orbital decay, but there's so little gas. I'm talking about so little gas left that maybe we don't need to worry about migration. Okay? Do we really need to worry about migration for super-Earths? Well, I'm going to overlay on this plot the surface densities required to shut off migration. That's given by this red line here. Everything above that is basically migration-free. There's just so little gas that the orbit shrinkage time, A over A dot, from type 1 migration, a.k.a. gas dynamical friction, is longer than the gas disk lifetime, which is measured in millions of years. Okay, so we're talking about environments here where migration really isn't an issue. And all of these debates that I've been part of and that I've had to listen to over many years, type 1 versus type 2 versus type 3, and how do planets survive, all of that, irrelevant for super-Earths in this picture. Okay, let me move on. With these strong depletion factors, then now the question is, can I still reproduce the gas to solid ratios of super-Earths, right? Which are not 1 part in 10,000 or 1 part in 10 to the 7, but more like 1 part in 100. And so this at first glance is a little scary, right? This is very gas poor. Not only that, but there's a huge range. It could be anything in this range. There's all this orders of magnitude of gas density allowed for formation. Can we still get the characteristic percent by weight atmospheres exhibited by super-Earths? So that's this calculation. This is just one chapter in Eve Lee's thesis. Eve's now a Fairchild Fellow at Caltech. In the summer, she's going to start her faculty position at McGill. So I'm going to give you her answer first, and then we'll talk about the underlying physics. But I'll give you the answer first. So what she did was she took a super Earth core, 7 Earth masses in this case, embedded it in a sea of gas, pretty low density, depleted relative to the minimum mass value by a factor of 100, and just calculated how much gas this core accretes, okay, versus time. So gas to core ratio, GCR versus time, and up it goes. She's going to truncate the curve at about 1 million years, because that's how long the gas disk lasts. And at the end of the calculation, she finds a GCR of about 10%. So a little bit on the high end, but I would say in the ballpark, right, for these super Earths. But you'll see, right, the nebula here, we depleted by a factor of 100. We need to deplete more to fit the parameter space which I showed you on the previous slide. So let's go down in depletion, or up in depletion. We'll reduce it by another factor of 10. Sign is right, or it's what you would expect. You accrete less gas, but not much less gas. It's barely nudged. And meanwhile, you've knocked down the nebular density by a factor of 10. We still need to keep going. Let's go another 2 orders of magnitude. Not moving very much. That's good. Let's go for broke. 10 million. You can keep going. No matter how you cut it, you always wind up with a few percent. And this we regard as an encouraging result, right? The answer, all roads lead to super Earths. That's good, because the universe is telling us that percent by weight atmospheres are everywhere in the universe. So there are significant, of course, as you can imagine, right, uncertainties. We don't really know exactly how gas disks clear out, but I don't really care, because there's this robustness. You might say, oh, well, I fine-tuned the cutoffs to be 1 million years. Well, I can cut it off at an earlier time. I can cut it. There are models out there where the inner disks, sort of collapse on a time scale of 10 to the 4 years, fast, these 2 time scale models. And I still get about 1%, which is what I want to explain the observed gas to core ratios. So there's this the growth is very slow. It's a characteristic power law growth, and I'm going to derive for you, maybe a few slides from now, what this power law is. You can get it in 2 lines. Yeah?
What happens if you don't deplete at all?
Oh, good question. If you don't deplete at all, the curve looks like this. If you don't deplete at all, sigma MMEN, the curve looks like this.
Oh, run away.
Oh yeah, bad news. Good news for giant planets, but terrible for super Earths. Yeah, great question. I'm going to get there at the end.
So
Yeah.
just so I understand your picture, so this doesn't work in the solar system because the classic view is, when we teach kind of classic planet formation, the Earth is formed by late collision of lunar mass objects, and the timescale for that is tens of millions of years.
Yes, exactly.
And so are you saying that that's also what's going on here?
Exactly.
But I have a small amount of gas which would be undetectable to my disk, so that the limits of 3 million years for disk dissipation. Or are you saying that actually I'm forming super Earths through collision much, much, much earlier than I did in the solar system, and all of this is happening on a timescale of 10 million years when there's lots of gas still left?
The former.
The former, okay.
The former.
So you're saying my disk observations are not, they are telling me that most of the gas is gone by 3 million years, but there's plenty of observational.
I don't need a whole lot of gas.
Right.
Right.
Okay.
Okay.
So the basic time scale for that late collisions of lunar mass objects that still holds, and all the action here is happening at 20 million years, 50 million years.
Yes. Yes. The way I like to say it is that this picture is basically the same picture as for the terrestrial planets, just staged a little bit earlier. And that was possible because, for some reason, which I don't quite understand, most disks out there, right, which spawn super Earths, they have higher surface densities in solids relative to the disk that made our solar system. So the cores, in both cases, the cores formed by major mergers. It's just that these major mergers happened faster, a little bit earlier maybe a factor of 10 earlier relative to what happened in our solar system. Okay? So in our solar system, same thing happened, just 10 times later when there really was no gas left. Okay? But otherwise, it's the same picture. Okay. Dimitar.
On the other hand, you're kind of a precarious situation here because you're 0.1 AU. So in some of those cases, you will just lose the gas over the following 2 to 4 or 5 billion years.
0.1 AU, I think, is right where the border is for, I think you were talking about are you referring to photoevaporation? Yeah. And people see that, right? And people see that. Inside of 0.1 AU, they're still super Earths, they're just small, they've lost their atmospheres. But outside of 0.1 AU, they've retained them. So we can do the calculation everywhere, 0.1 to 1, yeah. Yeah, I'll show it. Okay, Avi.
Presumably, there is a floor here because if I put zero mass in gas, you will have zero.
Yes.
So what is that floor?
Okay, good. So 0 is 0. Yes, true. That's true. Short answer is I can go up to about 10 to the 8 in depletion. And then the radiative convective boundaries for technical reasons, you sort of cool off instantly and you can't accrete anymore. So short answer to your question is we calculated it and it's 10 to the 8. Okay. All right, so why is it that it's so insensitive to the outer nebular density? I'm taking a page again from my